So on this second part of 9.5, we are still talking about the quadratic formula. So we're going to review again, just solving with the quadratic formula, just like we did yesterday. But we're going to extend that just a little bit and talk about something that we call the discriminant and how that can be helpful to us. Okay, so that's kind of the new or extension from yesterday, is interpreting the discriminant and what do we mean by that and how can that help us, right? So let me set up my pen here. The big thing is, there are a lot of situations where the reality is, you guys, that we don't need to solve the quadratic. Like, we don't need to know the exact solutions of the quadratic. We just need to know, does it have solutions? Okay? So, for example, we haven't done it yet, but yesterday, number 9, the word problem, is about a water balloon. And the first part of that problem asks, you know, when will that water balloon reach 9 feet? A height of 9 feet, okay? And so you solved it to find out when it reached a height of 9 feet. But the reality is that if that was really a real life scenario, you might be less interested in when does it hit 9 feet, and you might actually just need to know, does it get to 9 feet? Like, will it reach that height? You know? If you're if you're singing a water balloon and you want to make sure it hits your friend in the face and they're in the second floor balcony, right? You just want to know, is it going to reach their face, right? We don't care when, right? So that's just a silly example, right? But you could think of it as if NASA was launching weather balloons. There's just lots of different scenarios where the reality is we don't need to know when exactly it's going to happen and what those exact X values are. We just know, does it have any? Is there any solutions at that particular value, okay? And for that, we can use a very simplified version or little section of the quadratic formula that we like to call the discriminant. This right in here is the discriminant. The part that is inside the radical is the discriminant. Okay, so that's that part right there. And that expression under the radical sign, that b squared minus 4ac, is what really determines how many solutions our quadratic is going to have. And sometimes that's all the information we need. Okay? And the reason why that determines how many solutions it has is precisely because it's inside the radical. And now that we have played around with this enough, when we did 9.1 and we just overall practice simplified radical, and then also we've seen the simplified radicals with completing the square and the square root method and quadratic formula. Basically, we know that anytime I take the square root of any positive number, that's going to result in 2 roots, right? So I'm just picking some random a value. Any positive number, anything greater than 0, always has 2 roots. Whether they're nice, pretty numbers, like if I say, what's the square root of 25? Well, it's positive and negative 5. Or it might be really, unpleasant, irrational decimals, but it's still 2 roots. That's why we kept emphasizing, don't forget that plus or minus, there's really 2 roots. You remember that? Okay? So if that discriminant is a positive, greater than 0 value, then the entire quadratic is going to have 2 roots. So on that problem on the homework, if you finished it out, when you worked it out, that discriminant was positive, and you ended up, finding 2 solutions. Not only did the water balloon hit a height of 9 feet, but it hit it twice. Probably once on the way up, and then went past it, and then back on the way down. So it hit it twice. As soon as you see that discriminant is greater than 0, you know you're going to have 2 solutions in that quadratic. Okay? Now, if instead of it being greater than 0, it's exactly 0, well, the square root of 0 is just what? 0. And there is no plus minus option on that. Okay? So it's just 0. That entire radical pretty much just zeroes itself out. In that case, you end up with 1 solution. Just 1 real solution. It still has a solution, but it's only 1. And in fact, it's kind of neat. If you look at the quadratic formula, if this whole thing just zeroes out and goes away, does anybody recognize this little guy here that's left? All of that goes away. What are we left there with? Look at the numerator and look at the denominator. This is what we're left with. What formula is this? What did we used to find with it? The axis of symmetry. So yeah, so there's that connection, right? Because that means that the vertex is the solution, and the vertex lives where? On the axis of symmetry, right? So if it only has one solution, it means the vertex is that solution, and that lives on the axis of symmetry. Boom, there it is, right? Coincidence? Absolutely not. Math, right? So with all that said, so if it's equal to 0, then we have exactly one solution. I'll circle that again. And then last but not least, what if that part inside is a negative? Can we take the square root of a negative number? No, it has no real solutions. So if the discriminant on its own results in a negative number, then we know that this has no real solutions. Okay? So that's at the heart of today. There are situations where we don't need the exact answers or solutions. We just need to know, are there gonna be any? Does it reach that height? Does it equal that number? And that's all you have to do is pluck out that discriminant and decide, is my discriminant positive? Then it's going to have two real solutions. Is it exactly equal to 0? Then it's going to have one real solution. And if it is a negative value, then there are no real solutions that will make that true. Okay? So you don't have to use the entire formula. You can just use b squared minus 4ac. All right? Let's practice a few of those. And that's really this plus just practicing the quadratic formula and practicing just picking your own method. That's all we're doing today, okay? So determine whether the set of determine the number of real solutions in the equation. So all they want is the number of real solutions, not what they are. We don't have to solve all the way here, okay? So if we go through this kind of in a step-by-step, step 1 is make sure that it is set equal to 0 before you begin. So you pick the correct A, B, and C values. So set it equal to 0. Number 2, identify what A, B, and C are. Okay? And then for number 3, then use that discriminant to make your decision about how many real solutions it has. That's kind of our game plan, right? So if you look at number 1, is it already equal to 0? Yeah, so it's already equal to 0. We're okay. So let's identify what A is. In number 1, A is -1, B is 6, and C is 3. Everybody okay with that? Because they're not asking me to find the solutions. They just want you to say how many real solutions there are. I don't have to use the entire quadratic formula. I can just use the discriminant for that. Okay, so I'm going to use that b squared minus 4ac. It's up here on the board as well. Okay, and I'm just going to insert into this. So here, b squared is 6 squared minus 4 times -1 times 3. And then we just simplify this carefully with order of operations. So 6 squared, 36. And then a -4 times a -1 is a +4, and a +4 times 3 is 12. So the product of those three things over there gives us a +12. Do we agree with that? And then 36 plus 12 is 48. So my discriminant simplified to a +48. Therefore, that quadratic has how many solutions? 2 real solutions, right? So that's it, and that is, you're done here. 2 real, no, those are not your solutions. You would have to do the complete quadratic formula if you wanted to, like, do the full solution, right? Because that's positive, that's greater than 0. As long as this is positive or greater than 0, then I know I'm going to end up with 2 solutions, 2 real solutions. If you wanted to know what they were exactly, then you would have to use either the entire quadratic formula or one of the other methods that we've discussed, complete the square, factoring, graphing, square root. But here, they just want to know how many solutions there are, so real solutions. Okay. Let's try number 2. Is it equal to 0? It's equal to 0. So let's make this a little easier to read. So then let's identify what is A, what is B, and what is C. Is that okay with everybody? 1, 6, and 9? Okay, and then we'll just use the discriminant since we don't have to solve all the way. We just need to determine the number of real solutions. So when we insert that, we get 6 squared minus 4 times that A value, which is 1, and the C value, which is 9. And again, 6 squared, once again, is 36. And minus 4 times 1, which is still 4, and then 4 times 9 is 36. What happens when we do 36 minus 36? 0. So when the discriminant is exactly 0, then how many solutions do we have? 1 real solution. We have 1 real solution. Okay? Exactly 1 real solution. All right, how are we feeling about those? Okay, let's try this last one. Okay, so on this last one, is it equal to 0? Yes, let's identify A. A is 1, B is 3, C is 8. And then let's use the discriminant to decide. So if we insert the 3, the 4, the 1 and the 8 here, and simplify, we should have a good idea. So 3 squared, 9, minus, and then 4 times 1 is 4. What's 4 times 8? 32. And then if we do 9 minus 32, it ends up being a negative 23. There's our discriminant now. If our discriminant is negative, that means that in the quadratic formula, we would end up taking the square root of a negative. Can we do that? No. So how many solutions does this have? No real solutions. Okay? So this has no, don't say no solutions because that's actually not true, but no real solutions. It will have complex solutions that involve imaginary numbers, but it doesn't have real solutions, which is where our focus is. Okay, give me some thumbs up, down. How do we feel about that? All right, let's take it to just a little bit more practice. Look at 4, 5, and 6. So on 4, 5, and 6, it says find the number of x-intercepts of the graph of the function. Is that really any different than what we just found? No, because we know that the x-intercepts are the same as the solutions, right? In fact, we can see that over here in this slide. 2 real solutions is the same thing as 2 x-intercepts. 1 real solution means 1 x-intercept. No real solutions means no x-intercepts, right? So it's really the same question. Find the number of x-intercepts of the graph of the function. X-intercepts is when y is 0. So the first thing we do is we replace the y with a 0, and then we play the same game we just did. So practice 4, 5, and 6. I'll give you guys a couple minutes head start. So I'm going to start working it out. That way you can check your work. Once it's equal to 0, identify what A is, what B is, and what C is. And because we just want to find the number of x-intercepts, we don't necessarily need to know where they are. We can just use the discriminant. So in this one, it's going to be 4 squared minus 4 times negative 1 times 3. And this comes out to 16. Negative times a negative is a positive. This comes out to 12. So I get 28 on the first discriminant. Is that what y'all got? Awesome. If you got 28, you're in good shape. And if it's a positive 28 for the discriminant, then how many x-intercepts does this have? 2. So this has 2 x-intercepts. Okay. So that one has 2 x-intercepts. Let's try this next one. Number 5. We'll set it equal to 0 to find the intercepts. Identify A, B, and C, and use the discriminant. So we'll do 14 squared minus 4 times 1 times 49. Okay. And we square 14. How many of y'all have that perfect square already memorized? What's 14 squared? 196. Good. 196. And you may not have this one memorized, but when you do 4 times 1 and then times 49, that's also 196. Did y'all get 0 for the second one here in the discriminant? So how many intercepts is that going to have? 1. Just 1 x-intercept. All right. Good. Let's try one more. Let's see. This last one, we'll set it equal to 0 again. We'll identify what A is, what B is, and what C is. I'm also modeling how I want you to show your work. So this is what I'd be looking for. For credit, we've got B squared minus 4 times A times C. In this case, this is where it matters really to put parentheses. If you just get into the habit of always putting those parentheses, it'll be fine. But here, if you square that without the parentheses, especially on the calculator, you're going to get that wrong. So be careful there. Okay, so it's a negative 8 squared. That ends up giving us a positive 64. And then over here I have 1, 2, 3 negatives, so that's going to result in a negative. And it comes out to 72. So when we combine that, I get negative 8 for my discriminant. Is that what y'all got? And if I have a negative 8 in the discriminant, that means I'm trying to take the square root of a negative. Will that ever work? Not in this real world. Haha, real numbers, get it? So that means that this has how many x-intercepts? None. No x-intercepts. All right. Give me some thumbs up, some thumbs down. How do we feel? Okay? Okay. So before we do 7 through 10, which is really more practicing pick your method type of stuff, let's skip down to number 10, which is still more connected to this discriminant concept. So check out number 10 for me and see if you could problem solve or think through logically. This is a nice little sort of brain teaser or challenge here. You have a quadratic, but C, that constant, is a variable. It's missing. And we just want to know what would be a possible value of C that would make each of these scenarios true. Okay, so give a value of C for which the equation would have 2 real solutions, would have 1 real solution, and no real solution. So we may get different answers. Some of these may have more than one potential answer that works. So see if you can troubleshoot through that. So if you need a little bit of guidance on this, think about this, right? So I know that we don't have a C value, but do we have an A value? What about B? Yeah, so we have those. That might be a good start, right? So we know A is going to be 1, and we know B is going to be a negative 2. C is the one that we have flexibility or that we're missing or we have flexibility to choose, right? Also, if we're not fully solving, we just want to know about how many solutions, then which little formula should we use that we just learned? The discriminant, right? So I know that this discriminant right here would be kind of the guide here to decide how many solutions this is going to have. Now, so let's go ahead and plug in what we know, right? So we do know B. So B is a negative 2. And we do know A. A is 1. We don't know C. So if I clean this up, I really get 4 minus 4C. Is that okay with everybody? Now, in order for this to have 2 solutions, this right here, this discriminant expression has to be what? Positive, greater than 0. So you really could just almost, I know it said give a value, but to find your values, this is really what you're doing. You're trying to think of what value of C would make this side greater than 0 or positive. Yeah. I don't know, would 0 work here? Yeah, it would. C could be 0, right? C could be 0, and then I would have 4 minus 0, which is give me a result of 4. That's perfect. Any other ones that y'all came up with? Yeah. Could we do a negative number? Absolutely, right? We could plug in a negative here because then when we do a negative times a negative, we'll get a positive. We'll end up adding this, and we'll get a positive number, right? So how many of y'all kind of decided on a negative or on a 0? Good, yeah, that's it. And if you weren't sure, you could always just solve this out, right? And we could say, you know what, I'm just going to try to find what all the values are. We could do that and say, I'm going to solve for C here. And then I'll divide by the negative 4. Now, when we divide in an inequality, when we divide by a negative, this is good review. What do we have to do? Flip that sign. But here's at the heart of this. Any C value that was less than 1. Any C value. I could have picked a half, right? If I put a half in there, then 4 times a half is what? 2, and 4 minus 2 would be 2, and we would be good. 2 solutions. Anything less than 1 here would work. So if you picked anything that's less than 1, you're fine. It could be a half, it could be the 0, it could be a negative. Absolutely. Yeah. Well, this one says give a value. So if you just found like a negative and you plugged it in and it worked, then that'd be fine. But I'm kind of giving you why it works and the way that you could find it. Maybe if it said all the values, inequality would be a good way to think of this, right? What about the one solution, right? We already have this simplified version, so I'm going to use the simplified version since it's going to be the same here. But if we wanted this to be one solution, then we would want this discriminant to be equal to what? 0. Exactly 0. So does this one have more than one option? No, right? This one has a whole infinite list, right? Anything negative, anything less than 1 would work. Here, though, I have a lot more limitation. It's just only what would make this equal to 0. What would make this equal to 0? 1, right? Exactly 1. So C equals 1 would be the only thing that would work if I wanted to guarantee that that up there has only one solution, okay? And then very similar to A, what about the no solution? If this is my discriminant and I want to set that up and make sure that this has no real solutions, I would make sure that this discriminant is, well, the solution, C will be greater than 1. Yes, you already got the answer, but the discriminant, we would want it to be less than 0, negative, right? So we would want this to be less than 0, but most of y'all already kind of figured out this riddle. Then that means that any C value greater than 1 would make that happen. Does that make sense? Okay, good. That's a good thinking problem there. All right, so if y'all feel good about that one, then let's back up here. This is actually really more reviewing yesterday's lesson. Just the overall solve by any method. Look at the quadratic. Give it a second to kind of sink in. And think about what method would you think would make sense. And maybe not all of us will choose the same one, and that's actually pretty cool. But you have 5 options, and all of them you have to show work, right? But you could graph, you could do factoring if it's factorable, square root method if it works, but then completing the square and quadratic formula also always works. So think about which method you would pick and why, and try it out. Now this is solve the equation. So you have to solve it all the way. This is not a discriminant problem. Always make sure you read the directions carefully so that you are doing what you're asked. This is solve the equation, so we're getting full-blown solutions here. On number 8, I've played around with the magic numbers enough to know that that 7 times 1 equals 7, but 7 plus 1 is 8. So I'm like, you know what? This might be factorable. So I looked at this one and I was like, all right, let me see if this works. Oh yeah, if I make that a negative 1 and a negative 7, those multiply to 7 but add up to negative 8, I can factor this to just those 2 binomials. Right? And then if I have this times this equals 0, the solutions are going to be whatever makes this 0 or that. So what would be our solutions here? X equals 1 and x equals 7, right? So that was a really good choice for factoring, although you still could use all of the other methods if you would like. But it was a particularly good choice for factoring, okay? The first one was a really particularly good choice for the square root method. But you don't have to use that one, but if you can tell that's a perfect square trinomial, then you can jump right in. What about number 9? Is that a good choice for the square root method? No, right? That 3 is really throwing things off. None of that is a perfect square for sure. We could try to factor it. But we'd have to do the longer factoring method. 3 times negative 5 is 15. I'm not really thinking there's any factors of 15 that combine to 1. So, do you think this is a good choice for completing the square? Completing square? We would have to divide through by the 3, which is going to give us fractions. And then the middle I have 1. I'll end up with a 1/3. I'll have to square that. I mean, you could. It does work. It works. But I'm not sure that it's a really pretty choice for this one. I tend to reserve my completing the squares when A is 1 and B is an even number. If I can avoid all the fraction stuff, I will. Okay? So you might graph this one, but then I'd have to go grab graph paper, grid, yada, yada. I think quadratic formula is a pretty good choice. Raise your hand. How many of y'all did quadratic formula here? Yeah, so I think so too. Honestly, you know, by the time I get the graph paper and the ruler and all that out, I probably will have already finished doing the quadratic formula. But, and again, most of them work for all of these, graphing, completing the square, but I think this is the path of the smoothest path to victory here. Okay, so we'll do negative b plus or minus the square root of b squared minus 4 times a times c, all of that over 2a. And then that gives me a negative 1 plus or minus. 1 squared is 1. 4 times 3 times a negative 5 gives me a positive 60 when that's all said and done over 6. And then what's 1 plus 60, guys? 61. And I believe 61 is a prime number, so I don't have to worry about perfect squares or any of that. And that's the other nice thing about this quadratic formula. It didn't say I had to leave this as a decimal. It's actually more work to go to a decimal. I'm just going to stop. That's a simplified radical answer. I'm good to go. Okay, simplified radical answer is totally fine as long as it's simplified. Okay. Well, if you grab your calculator, this one didn't specify simplified radical or decimal, so if you then grab the calculator and solved it, just entered everything in there, and your answer is right, you'd still be okay. On the test, though, you will be asked for both answers, the simplified radical and the decimal. So you want to make sure you know how to do it this way, okay? All right. All right, how do y'all feel about those? So that's just the pick any method. There is no wrong method. I mean, unless like you try to factor it when it can't be factored, but you know, there's no wrong choice as long as it works. You just have to show the evidence of your work. But you can see here how certain ones lend themselves more easily to certain methods.